crowded and cozy over here. So okay, I'm going to talk to you today about writing safe and secure code, and I'm not going to mention that other programming language at all. So I am Daniel Stenberg, going humble here, but I got this a few years ago. I don't work at Mozilla anymore. I work for Wolf SSL these days. And you may know me mostly for my work with curl that I've been doing for a while, like 3 years or so. And it so happens that my code runs in a lot of places, roughly 6 billion instances perhaps or so, give or take a few. So every one of you run my code in things like 150 million cars and 200, or actually pretty much 500 million games these days, and 500 million TVs, and basically 1 billion Windows 10 machines, or 3.5 billion mobile phones. So that's me bragging about them. So okay, I'm here today to well, basically talk about how to write the safe code. How do we get our code running on all these places and not making everything into terrible chaos? Oh, I do that sometimes anyway, but still. So, writing safe code and doing things correctly, it's not by coincidence, right? It doesn't just happen so. We have to actually make an effort to make sure that it ends up secure and safe. So, it means that every one of us have to care about it. We have to put up a little extra, make sure that we have the routines and everything there, and make an effort. So, this is really about time, that we finally, in this day and age, start being a little bit concerned about this and fixing our code, our own shit to start with. And I'm not going to tell you a lot about things today that you don't already know. I'm just going to emphasize, and so you get to hear it again from me, because we like saying things many times. So, but this is my way of saying how we should do things to make sure that they're secure and safe. And we start out by writing things the correct way, of course. And when we do things like we provide APIs and write tools for users, we should, of course, provide them with APIs that are easy to use and not mess everything up if they follow what they think is the easiest path forward. We should provide them with good defaults. You know, the power of the default is very strong. You know that most users will just stick to the defaults if we provide them with that. So the defaults should be safe and secure, of course, for your APIs and apps and whatever. And we should document everything a lot. And of course, that's a good thing. We're here talking about fast and open source. Open source is good. We can have the code live a long time. Long time means long time to write documentation. So over time, we will have a lot of documentation, and that's good. And we, of course, get rid of all the warnings. We don't compile things, get a few warnings. No, we fix the warnings and then move forward. There's this notion sometimes that comments shouldn't be necessary if you just write your code correctly, which I think is a bit amusing, because just, you know, fast forward 10 years, reading your own code from 10 years ago, not that easy anymore. So, of course, comments is good for everyone. We should use it a lot. That makes it easier for everyone to understand the code. Understanding the code is essential to writing secure code. And then, of course, one of these golden things is assert. You should use them a lot. And of course, we release code as open source to get more eyeballs on the code, more people complaining when it doesn't do what it should do, and it has the opportunity to survive for a much longer time, right? It doesn't have to die just because your project dies at the end of the year or whatever. It'll continue working on. And of course, this goes the other way around. You'll benefit from using someone else's open source instead of a proprietary one for basically the same reasons. So if you then do follow this when you write code, you then, of course, review the code, right? You review everything that is written. So you don't just commit something to your Git and be happy with that. No, someone else reviews your stuff before you merge it. And you follow the style guide, right? You're supposed to write code that is easy to read and understand. You don't get points for being clever. It's not good to have everything crammed up in a little space. That's not good code. You're supposed to be able to read the code and understand what it does. If you don't, you better write a little extra, add a comment, explain it, try it again. And we use the same style everywhere. You don't mix code styles. You don't read a novel, right, when they mix the style in a novel or whatever you read. You want the same style throughout the code. Again, to make it easier to read and understand and follow. You don't need to see that there are different peoples involved in writing the code. You don't even have to like this style that you're using in your project. Just use the same style everywhere, and it becomes easier code, less problems, and you'll find those bugs and security problems easier. And a little pet peeve of mine, use a sensible commit message template. Actually provide good information in that's fix is not a good commit message. I mean, you're fixing something now, right? It might sit there in your Git repository for, who knows, maybe 21 years into the future. And it is good to have that message to be, for all those other 1,000 eyeballs that are going to read your commit message, they will enjoy that you actually spent 10 minutes in producing a good and quality commit message. Fix is not good. Explain where you did it, why you did it. And of course, when you review something, you make sure that the author of the code follows this style, the style guide of the code, the template in the commit message. Quality code, quality commit message, easier to read and understand and follow. And once you've written the code, you review the code, you merge the stuff, and you start testing it. So of course you have a lot of tests, right? So you have your unit test, you verify that your functions actually do what they're supposed to do, and you put the functions together, and they actually work together too, and your bigger things work together as well, you know, the same way we always do things. So, and of course you can test the documentation as well. That's a harder part, but reference documentation, and you can make sure that all the links are there, that you don't reference stuff you removed and things like that. Harder to test the documentation, but still valuable to do for as far as you can. And of course, manual tests is something we all rely on in the end. You don't get enough tests of your stuff until you release it and onto the world, and then suddenly all the users start complaining because they use the stuff in ways you didn't test for anyway. But well, they find the bugs, we add a test, and we start over again. For the next release, maybe we'll catch that bug. So this is how we do it, right? And once we wrote the code, we reviewed the code, we've tested the stuff, we've written these tests, and yeah, that's good, right? Yep, and then we start to tormenting the code, right? This doesn't just testing stuff with your own creative ways of testing the code. That's far from enough for finding your problems. You need to add the fun tools like running your code with, if you're using C or C++ or whatever, you want to run everything with Valgrind. You want to add those sanitizer tests or checks, address sanitizers, undefined behavior, and integer overflow sanitizers with Clang and GCC. Excellent tools. You want to run your static code analyzers, and you want to remove every defect. There are many static analyzers, of course, both open and not so open. A great way to smoothen out things. If they found defects, you better find a way to write it in a different way. And then, of course, once you've come all that way, everything is great and fine, then you throw on the fuzzers on your code, and you start fixing all those bugs that the fuzzers find, because that is certainly the next level here. Everything can be green and no zero, or rather zero defects up until this point. Throwing the fuzzers on your APIs, that's the next level of fun for a time onwards from that point. Fuzzers then basically throwing a lot of shit on your APIs, making sure what happens, and then fiddling the data, try it again, try it again, try it again, try it again, until it finds something that wasn't intended. So, and once you've fixed all that, well, fuzzing never really ends, but you can at least, once it hasn't found anything for a good while, you're in a fairly good spot at least. But of course, your code keeps on changing, right? So even if you followed all these steps up until this point, you're not done at this point. So we need to keep doing this all the time on every commit and every pull request we do all the time, right? All of this all the time, non-stop. Easy peasy. So, in the curl project that I spent some time on, we try to do all this actually. So we have, for every commit, every pull request, we do 50 builds roughly, or test rounds. And we test for code styles, we test for indenting, so there's a red cross if you don't follow the style, if you're indenting the code the wrong way, or if you're putting your braces on the wrong position on the lines, or having too wide lines. So we do a few thousand tests per build. That's like 50 builds times 1,000. So it takes a while. We build on roughly, well, I think we have a little over 10 platforms, limited mostly then by what kind of architectures we have access to from build farms and volunteers. So it makes it take roughly 20-25 hours per commit in CI build times. That's basically total CPU time, so they're actually running a bunch of them in parallel, so they don't always take 25 hours until they're done, but sometimes they do. That's a little bit annoying, but what do you do? So in the project, I just wanted to mention then what we do use tools to accomplish all this. So we like Valgrind, as I mentioned before. It's an awesome tool to find some things, and we of course run Clang, all these sanitizer things enabled builds, and we use Clang Tidy, which is, it's a sort of a combination, but it adds some extra linting mumbo jumbo. I'm not sure exactly what they put in each of these tools, but they find the different problems actually. And we have also our own torture tests, which are funny. I just wanted to mention that because so when we run we have our own memory debug system, so we instrument basically all functions that can return memory or handle dynamically. And you run the tool once and count the number of times we return memory, 125 times. And then we run the tool again 125 times and let each of these occurrences fail one at a time, and make sure that everything works, even if every malloc or fopen or whatever returns failure. An excellent test actually to test exit paths from failures. So, and then we of course use a lot of static code analyzers. Scan build, again, another Clang tool, but that too finds other stuff than the other Clang things. And we use the LGTM static code analyzer. That's a free one, easy to integrate with GitHub, for example. And the codice is similarly easily accessible. Not sure, those two are possibly the weaker among the static code analyzers. Coverity being the grand star among static code analyzers. That's of course not a open tool, but it's freely available to open source projects at least. Really, really the best C++ code static code analyzer to use. So when that goes 0, you're in a good place, and when that is there, as I said before, you go fuzzing, and we're part of the OSS Fuzz project, which is an excellent project run by Google. So they basically have a lot of machines. Google has a lot of machines. Maybe you didn't know, but they have a lot of machines, and they run fuzzing. So, and they have adopted a huge bunch of open source projects that they fuzz. So they have a whole army of machines fuzzing our APIs nonstop, and they have found a lot of fun things. It has trickled down, so they haven't found a lot lately, which is great. So initially, I think they pointed out at least 4 different security problems and a bunch of memory leaks and whatever crap else. So an excellent project. And of course, that sort of goes, if you do your fuzzing right, you can find a lot of things. But fuzzing isn't always easy, and it's resource intensive, and it takes a lot of time. Then it's good to have a lot of machinery. So we use then a lot of free CI services. Actually, all of these tools that we use in the curl project, everything here is provided for free. So we don't pay for any of this. So Travis CI, AppWeyer, Zero CI, and we have a bunch of volunteers running build bots. So a lot of things running. So basically then, just to go back to what I said before, we have a few policies in the project. We fix all warnings, which is easier said than done, because we support basically every 32-bit architecture you can imagine. So having the code run warning-free everywhere, it's a little bit of a cat and mouse game that we never really completely managed to come out alive from. So yeah, we have a few warnings, but yeah, basically we fix all warnings. And we don't leave any defects detected by any of these tools. And we always build everything with as strict and most picky warning compiler options that we can find. Anything that is suspicious, we fix and make them not complain and warn about anymore. And of course, we have as many tests as possible, which is funny because, as I said, we use all these free-tiered CI systems, and that is a bit of a challenge now because we're running into the time limit for some of them. So it's going to be expensive when we go further, I think. Or we're going to have to rearrange our testing systems. And of course, we fix security issues as soon as we can. I'll get back to security issues. So, of course, this is expensive. I mean, doing this in your project, it takes a lot of time, effort, and yeah. So you have to spend effort, time, and energy to do this. But of course, not doing that makes you suffer from all sorts of fun things that you will end up. Maybe you won't write exactly these flaws, but these flaws are, of course, the results of security problems in development stages of different kinds. And well, here's one just from the other week. And a favorite one, and even if you do end up with one of these security problems, you can also opt to fix them in not so good ways too. So even if you are Cisco, you can find security problems and you might fix them, but they didn't follow the review step in my guide here, I think. But they fixed the immediate flaw, right? So, well, and then even if you follow all these steps, you do everything right, bad things will happen for sure, because we're all humans still, we write everything this manually. So flaws will happen, and we just have to recognize that this is what's going to happen, so we will just act on it immediately when we get to know about it. And we own the problem, so with that, we fix it. We ship a new one. We try to learn something from it, right? We add bugs, we try to correct our procedures. How did this flaw end up in our code? What's wrong did we do? What can we do better next time? Not always easy to learn, because everything moves all the time, so maybe the next time is completely different. But still, things are not going to be good if we don't do that. So we just have to shape up. So just to wrap this up then, I have this fun, easy remember word, right? Easy to remember. So that's basically just what I've just said in a simple, easy to say word. You write clean code, right? And someone verifies it by reviewing it. And then we test everything, we torment it, and we act on the mistakes that slipped in anyway. That's what I wanted to say. Thank you. And I have room for questions if something wasn't really extra clear.
You said you are not going to talk about the other language, so I won't be rude and I won't talk about that language at all. But what I would say in general is that you talked a lot, on one slide at least, about automating things, and actually a lot of slides where you were talking about automating tests and all that, and vulnerabilities and all. But wouldn't you agree that it would be better in this modern world to use tools in general, not just that language, but tools in general that make it easy to write tests, that make it very secure to not make memory mistakes? And
of course. I mean, I mentioned like a whole bunch of tools, right, that make this easier. Tools that we didn't have for maybe 10 years ago. So of course the tooling has become much better in modern times. But saying then sort of, hallelujah, we're going to be saved by a magic new programming language that is going to work for Windows or Linux, that is not the solution short term for any of these problems. But I'm sure that we can fix a lot of problems by switching out languages to some other language in the future, and more tools. I built curl using a library written in Rust. I compiled it 2 months ago, and today on the train down here, I tried to build it again. What happened? Rust changed, right? Rust up. I had to upgrade my Rust because in 2 months it had grown old. So yes, Rust.
I think what happened was that it found problems in your code that it didn't found before.
Anyone else?
I'll offer you a bonus. If you do things right, you can get a thing from the king.
Did the king have any idea what you were receiving it for?
During this evening, with this award ceremony thing, I sat across him during the entire dinner, and there was a lot of videos and stuff about what I'd done and everything, but it's very complicated. Does anyone in my family know what I'm doing? Does it, maybe. So no, I don't think the king knew what it was. I don't think basically anyone else did either, so no.
Did he ask you to use Rust?
That's what I got. Make it into Rust next time. Thank you.
Right, thanks. We will start the next talk a little bit ahead of schedule, so in about 5 minutes. So don't miss out on that if you want to see that talk. Thanks.